Well, Earth calling thermo students. Earth calling thermo students. Come in. Come in, thermo students. Nobody's on board yet. So we'll just be patient. It's early yet. It's 8:28 on my Timex. And we're going to study control volumes today. But first, let's wait and get some students on board. Right now, we don't have any. But we'll patiently wait here. Oh, we've got Megan. Megan's on. Hello, Megan. Hello, Megan. Megan, unmute and say hello. Yeah.
Gabriel and I are going to go get shots and go see Huddy and Chevy.
I wish I could go.
Well, you're busy.
Yeah, I am.
Ta-ta.
Ta-ta. Well, we only have me and Megan so far. Megan, unmute and say hello.
Hello.
Oh, hi. Yay. Good going. How are you today?
I'm doing pretty good. How are you?
Real good, actually. We're going to study control volumes today. Megan, do you know what a control volume is?
It would be a system that's volume stays constant.
That would make sense, Megan. In fact, I think a lot of people think that, but it's not true. A control volume, strangely enough, can change its volume. Nope, that's not what a control volume is. But you've learned something already. You've learned what it isn't. That's good. I wonder if your book tells you what it is. Let me look in the book here. If worse comes to worse, we could read the book. Let's see what it says. Control volume definition, page 2. Okay. Well, they kind of tell you what it is, but it's really on more like on page 3 in my book. Hey, we've got another customer, Parker. Welcome. Yeah, hello. Welcome to Thermodynamics for Wednesday morning.
Thank you.
Yeah. Good going. Yeah, there's Parker. Good going. Well, let's. Oh, hey, I've got another customer there, Cameron. Cameron's with us. Let's see if I can make this picture bigger here somehow. Okay, what's the secret here? Do I click on this little blue thing, you think? Oh, gee. Hey, there it goes. Yeah, there it goes. How do I get rid of this little tiny picture of myself over in the corner here? Be nice to move that down. It's just kind of in my way. Ah, well, I don't know how to do everything. But today we're going to study control volumes. The really big topic is the idea of a control volume and see what it is. It's a volume. Okay, we got a volume, and inside that volume is some stuff, is some mass. There's some mass in there. We call that our system. It could be a lot of things. It could be a solid or a vapor or a liquid. It could be oxygen or 100 other things, okay? But and it can have it can do work. It can actually expand. The volume doesn't have to stay the same. It can expand and do work, and it can have heat transfer in or out. A control volume can have heat transfer. But the key idea with a control volume is that it can have mass going in and or mass going out. Whereas a control mass, a control mass cannot have any mass going in or mass going out. That's the big difference. Control volume can have mass going in, and it can also have mass going out. So now you know what a control volume is, and some examples are, well, we're going to study nozzles and throttles and heat exchangers, I hope. That's kind of ambitious, but we'll do the best we can. But there's other things like boilers, for instance. See, a boiler has a liquid water going in and vapor, steam, water in the vapor state, like steam coming out. But it's got mass going in and mass going out. It's a control volume. A boiler is. That's what we're going to study now. See, up till now, we've talked about control masses. They can't have any mass going in or out. Like with a, here, I'll draw you a picture. Like we've been drawing these piston cylinder things. See, piston cylinder deal like that is a control mass. Whatever you have in here, like maybe some vapor, it can't get out. There's no mass going in, there's no mass going out. But see, a control volume, that could be something like when we study nozzles, there's a picture of a nozzle. And see, nozzles have mass going in, they have an incoming mass going in, and they have an exiting mass going out. So nozzles are an example of a control volume. So are heat exchangers and 100 other things. Well, let me see how many customers we've got right now. Let's see here. Oh, we're doing great. We've got Cameron and Bear and Aubrey, Parker and Megan. There might be more here. Let me scroll down here and see if there's more. Okay. All right. Trying to scroll down. Here we go. Yeah, we have Stuart too. Yeah, Stuart's with us, and Roxana. We got a good crowd. Well, we tried to put the YouTube video on. Somebody asked me about that. I forget who it was. Go ahead.
Yeah, it was me.
Was that that was my friend was that my friend Spencer? Was that who it was?
No, it's Parker.
Parker, were you able to successfully see the video you talked about?
I haven't looked yet.
Oh, okay. Well, it's supposed to be on there. You might take a look later.
Okay.
Yeah, I think we've got those videos on there. Okay. We're going to get started on this exciting lesson today about control volumes. But before we do, did anyone have another comment or question? Nobody has a comment or question. Okay. Well, let's just launch into that. Now here are the topics. We're studying control volumes. It's a whole chunk of our course. See, we've been studying control masses. Look at here, control masses, and that's a big chunk of our course there. Get this out of my way. There we go. But now the topic is control volumes. Okay. Well, to understand control volumes, we got to understand mass flow rate. So let's talk about that now, mass flow rate. And then we're going to talk about the first law for control volume. See, it's different. Then we're going to talk about these different devices. Okay, unless you have any questions, we're going to talk about mass flow rate now. All right. The topic right at this moment is mass flow rate. Now there's an equation. It's called the mass flow rate equation. It's in your book. It goes like this. That's it. That's the mass flow rate equation. And let me show it to you in your book. Let's see if I can find it here. Mass flow rate equation, chapter 4, and it's on page I can't seem to find it here. There it is. I found it. It happens to be on page 113 in my book. Okay. It's in the middle of the page. But now you need to know what everything is. This M stands for mass, but when you put a dot over it, it stands for mass per time. The dot refers to dividing by time. And the name of that with the dot over it is mass flow rate. That's what that is. That's the mass flow rate. Now this A here, that's area. That's the area through which the mass flows, okay? And this V, this dark V there is velocity. See, there's 5 different V's in this class, and you can get confused. There's a little v, and there's a capital V, and then there's this dark, bold type V for velocity, and then there's a capital V with a dot over it, and that's called volume flow rate. And there's even one that's called molar specific volume. We never use it, so I just mentioned it, but you can forget it. Mainly, you just have to worry about those 4. But see, they have different units. You know the units for that, and you know the name of it. It's called specific volume. And then you know the name of that. That's just volume, and it's cubic meters. And this is velocity, and that's meters per second. Now this here is volume flow rate. And what that is cubic meters per second. So we got to keep all those straight. That's how come they write this velocity with a different kind of a bold face so that you don't get it mixed up with the other V's. You can go through those units and make sure they work. Here, let's do that. Let's make sure these units work. See, this here is kilograms per second. That's mass flow rate. This here is square meters. That's what area is. Area is always square meters. Velocity is meters per second. And specific volume is cubic meters per kilogram. Now you stare at all those for a while. Now wait a minute. That didn't work. So I did something bad. No, I didn't. No, I didn't. It works. See the kilograms go up in the numerator, and then the meters all cancel out, and boy, Jove, you come up with kilograms per second. So that the units work. That is called the mass flow rate equation. Ta-da, and there it is. Now, there's another thing I was telling you about, the volume flow rate. Let's talk about it.
In the mass flow rate equation, what does the A stand for?
Oh, thank you so much. Was that Megan or Roxana?
It was Megan.
It was Megan. Megan, that A stands for area, and area is in square meters.
Okay, I was just making sure.
Yeah.
That's what it was.
Thanks for asking. Now, let's see, where were we? What was I going to do here? I forgot. We were going to tell you about volume flow rate. Now remember, little v is equal to big V over mass. And see if you can get to here with me. Big V is equal to m times little v. I bet you can get from there to there, students. I know you can. Now watch this. We're going to do a sneaky trick now. We're going to put a dot over that and a dot over that. Now this right here is the volume flow rate. And it's equal to the mass flow rate times the specific volume. So good going. We have another equation for the volume flow rate. Well, so what? Well, we could work a problem. Let me work a problem here. Okay. I think it's I want to work 410, yeah. Let me find problem 410 and we'll work it. That'll be fun. Okay, I'm looking in my book. If you have a book, you can look up problem 410, and here, we're going to do it now. I just need the room to work on it. This is problem 410. It's in my book on page P28. I don't know why they put P on. I guess P is for problem, maybe. They have a section in my book for problems, and it's P28. It says a large brewery, that's hard for me to pronounce, brewery. Well, I tried. A large brewery has a pipe of cross-sectional area 0.2 square meters. So here, let me write some stuff down. Here, I'll draw you a picture of the pipe. There's a pipe here. There we go, a little dashed line there. And the area of the pipe is 0.2 square meters. Let me keep reading. Flowing carbon dioxide. Oh, okay. Well, we're going to have carbon dioxide coming in and coming out. And coming in, it's 1,000 kilopascals. Let me write that down. 1,000 kilopascals, 0 degrees Celsius. With a volume flow rate of 0.3, they're giving us the volume flow rate, and they say it's 0.3 cubic meters per second. They gave us the volume flow rate. Find the velocity and the mass flow rate. They want to know the velocity and the mass flow rate. I'll put those in my little cloudy unknown cloud here that we want to find. Well, in order to do this, we're going to have to find little v, the specific volume. Now, we're just going to go to the back and look it up. Go back here and start snooping around and looking up carbon dioxide at 1,000 kilopascals, 0 Celsius. Here it is. It's 0.04799 in the tables. This happens to be table B.3.2. Now I'm going to pause now for 60 seconds. And I want you to find that, as many of you that can. I want to make sure that I got that right. All right, I'm going to shut up. You look it up. It's in the CO2 tables. Carbon dioxide, table B.3.2. Find it. And then I need somebody to say, they found it. And what about, I'm always picking on Stuart. Well, what about my friend Stuart? Have you found it yet, Stuart?
Yes, I did.
Wow, and did I get it right?
Yes.
Good going. Well, I bet some others have found it. Okay, well, let's write our equation. Now, the equation goes like this. And this V dot thing is equal to, it's equal to M dot times little v. Hey, well, looky here. We got the little v. Oh, but wait a minute. Auga, look at here. They gave us this, didn't they? They gave us the volume flow rate. Okay. Well, look at here. If you got an equation that you know that, you can solve for m dot. So that's one of the things they wanted. So here we go. M dot. You guys took algebra. You know, if you know 2 out of 3 things here, you can solve for it. Well, let me do that and see what I get here. Okay, I'm going to take 0.3, and I'm going to divide by 0.04799. Well, I got an answer. I'm getting mass flow rate is 6.2513 kilograms per second. Hey, we just found m dot. We're doing great, but they wanted the velocity. Okay, well, why don't we write the equation for the mass flow rate? The way it goes is A V over little v. Now we know m dot, we figured it out. A we know because they gave it to us. V we know because we looked it up in the table. So we can solve for velocity. Yeah. Look here, here's an equation. We know everything except the unknown velocity. I'm going to solve that now. I'm going to plug that in. And I'm going to get the velocity, and I want you to do the same thing. So here's your m dot. That's called the mass flow rate. And then you know the A, they told you the area was 0.2. And there's, okay, do it. We're going to find our velocity. Here goes. All right, m dot is that times V. And then you'd have to divide by the 0.2. Well, I got an answer. I got 1.5 meters per second. That's the velocity of that carbon dioxide as it moves through that pipe. So we've studied mass flow rate a little bit and volume flow rate a little bit. But I need to hear at least 2 students say, uh-huh. I need to hear 2 uh-huhs to feel good about this.
That's what I got.
Yay, there's one.
Same here.
Yay, I bet we did that right. Okay, well, let's go on to the next topic then. Unless you had a question, I'm going to erase this and we're going to go on to the next topic. I still have a little box over here that I'd like to get rid of, but I don't know how to do it. Oh, wait, there's a minus sign. I don't know. Maybe I better not. Can you guys still hear me talking okay? I hope so.
Yeah.
Good, good. Okay. All right. Now, the next topic is the first law for control volume. See, it's different. Let me make some room here. The big topic today is control volumes. See, we've been studying the first law for control masses. That's what we've been studying. And it kind of goes like this in the big letters. It goes like that. That's the first law for control masses. But now the first law for control volumes is more complicated. It's a little bit nasty. Let me write it for you. And I'd like to show you where it came from. But see, it goes like this. I forget how to write this. I'll just do it like this, I guess. Uh-oh, I'm running out of room here. But that's basically it. That's your first law for control volumes. Notice it's longer, isn't it? This is kind of short and sweet, but this has got more stuff in it. You know why? Because it can have masses coming in and masses going out. The mass has energy. Did you know that? If you have a chunk of mass, it's got energy. And if mass is coming in, that's an incoming mass. See that? Well, actually, that's an incoming mass flow rate is what that is. And if mass is coming in, it can change your energy. And if mass is going out, see, that's what that is. That one there is exiting mass flow rate. And if mass goes out, you can lose some of the energy that you have. So that's why it's got all these other terms. Now, this one doesn't have any dots on it because it's not per time. But see here, what they've done is they've taken this one, they've divided by time. And what you get is a rate. This is the rate of the change of your total energy. This is the rate of your heat transfer. It's the heat transfer rate. And this is the rate of your work, the transfer of energy by work. Actually, the name of this is power. It's work per time. And you know what, you've studied that, you know what power is. It's the work per time. That's what that is. It's the work per time, which is power. Now, if your system is doing work on the environment, the power is positive. But if the environment is doing work on the system, the power is negative. Now, with a heat transfer, if energy is being transferred into your system from the environment, that's considered positive heat transfer. Well, in this case, heat transfer rate. But if energy is being transferred out of your system, that would be the heat transfer rate going out. That's considered negative. So this is what we're going to show you. The first law, probably the most important equation in the course. Now, I think I've said that before, but I was talking about this equation here, but really they're the same equation. They're the first law of thermodynamics. They just apply to different systems. This one is to a control mass system, whereas this one is to a control volume. But we got to learn this because a lot of things are control volumes, like boilers, for instance, like pipelines, like turbines, like nozzles, which we're going to study hopefully here in a little bit. Okay, so here goes. We're going to study that. Probably need all the room I can scrounge up here. Now this is going to be a little bit boring, but the first law is so important that I think it's worth spending our time on so that we'll understand the first law. Okay. Let's suppose you had a control volume. You know, I'll just kind of fake this. We'll say this is a control volume. And this is going to be before. We'll have a before and after, okay? And here's your control volume. Before, and over here, here's your control volume. Now, I've told you that the volume could actually change. It doesn't have to be the same. It's just that you have mass coming in and mass going out. Now, this is your control volume after. And see, here's the thing. There's a little chunk of incoming mass right here. We'll call it MI. And it hasn't gone in there yet. But here, this is that mass has gone in. It's just penetrated and it's inside your control volume. But what happens here is you have some exiting mass. We'll call that ME. See, it was here inside, but it hasn't exited yet. And here it exits. It exits. Yeah. Now we'll just make up some numbers so you'll understand. So suppose this was suppose you had 12 kilograms inside your control volume, and suppose you had 3 kilograms that's coming in. Well, when the 3 goes in, that'll make 15. Suppose 2 kilograms go out. Now, if you had 15 and 2 go out, that means you got 13 kilograms in your control volume. But see, 2 went out. Does that make sense? Let me go through that again. You got 12 kilograms in your control volume. 3 kilograms come in. That makes you 15 kilograms. 2 kilograms leave. They leave your control volume. That means you've got 13 kilograms now in your control volume. That makes sense to everybody, I hope. And what I want you to notice is 12 and 3 make 15, but 13 and 2 make 15. You know what? That's the same mass. If you put a red boundary around this, if you put a red boundary and call that a control mass, and put a red boundary around this, you know what? That's the same mass, isn't it? That's the same 15 kilograms that you started with. And so you could use the first law for control masses. I don't know if you can see that red color. I tried to draw that with a red color. Let me try a little harder here. See, what I tried to do is put a red color around this. There we go. Can you see the red color now? Yeah, I think maybe. And I put a red color around this one. And see that there's 15 kilograms inside that red color boundary there. It's the same 15 kilograms in both cases. So we can use this equation here now. This is our first law. for control masses. If you want, you can put a little CM here underneath those to remind yourself that we're dealing with control masses. Now let's look at this. You know what this is? This is final minus initial. You guys know that. That's final minus initial. That's what delta always means. And now what I'm going to do is I'm just going to write them out. Here's the final. This is afterwards. And that includes both of these. So you could say this is the final total energy in your control volume. This is going to take about 10 minutes to do this, but I think it's worth our time. But see, the final not only has that, but it has this exiting mass times its internal, its kinetic, and its potential energies. So that's this whole thing here is the final. And now we're going to subtract the initial. Now the initial is going to have the initial total energy of your control volume plus this 3 kilograms that's coming in. So that would be your incoming mass times your incoming specific internal energy plus your incoming kinetic energy plus your incoming potential energy. All I've done so far is just write this term here. I ran out of room. Now here's my equal sign. And now we're going to write our Q and our W. Now it turns out that the heat transfer of your control mass is approximately equal to the heat transfer of your control volume. So I could substitute on this right-hand side, instead of writing control mass, heat transfer, it's going to be pretty close to the heat transfer of the control volume. The reason for that is heat transfer depends on surface area and change of temperature. And your control volume and your control mass have approximately the same surface area through which the heat transfer takes place, and the same difference in temperature between the environment and the system. So you can get away with that, but for the work, they're not equal. The work of your control volume, it's not equal. It's equal to this here. Well, let me write it out for you. Work for the control volume here. Yeah, here we go. I got room down here. Maybe you can see this. The work done by the control mass is not equal to the work done by the control volume. It's equal to the work done by the control volume minus some terms. A little bit complicated. This is explained in your book. And let me see if I can show you what page that is. In other words, you can't just stick the work done by the control volume in here. You've got to stick all this stuff in here. But let me show you where that is. Let's see. Chapter 4. It's on page, I think it's 115. Yeah, there it is. Page 115 or 116. Yeah, okay. This is explained on page 115. You could read it in your book. I don't have time to explain everything. But see, if you substitute that in there, we're going to put in this work of the control mass. It's equal to all this stuff. Okay. Well, we can do that. All right, here goes. I'm going to put all that in there. Now that's all that'd be all this stuff. See it? A little bit of algebra here. But by the way, they do this whole thing in your book. You guys could read, this whole thing in your book. Let me tell you where that is. Maybe I can find that. I hope. It looks like it's on page 116. Yeah. Starts on 115 and it goes to page 116. You guys could read this in your book. Now, did I get everything in there right? I wonder if I did. Yeah, I think I did. Okay. Well, now we got one big humongous equation here. It starts here, it goes through all this jazz. And there's the equal sign, and there's all this stuff here. And now you have to combine some terms and use some algebra. And I think I'll skip a step because I'm running out of room here on this board. And I'm just going to write down dot, dot, dot. That means I skipped an algebra step. But if you take all this, you can just combine terms. You guys took algebra in school. And here's what you come up with. We'll put a 2 under here and a 1 under here. See that E2 control volume, E1 control volume. I'm putting that over on the left side of the equation. There's my equal sign. And now I'm going to put all this other stuff on the right side of the equation. And here's what it is. And we're almost there if you'll just have a little faith here. Uh-oh. I'm running out of space here. We'll tack it in down here someplace. That's supposed to say PE, potential energy. I don't need an extra one here. I think I stuck an extra term there. That's not right. There we go. Whoops, I forgot. No. I'll get this right in a minute. Yeah, now I have that right. Uh-oh, I'm running out of room again. Uh-oh. I think I'm gonna make it though. Whew, barely made it. Gee, I don't know if you can see all that. Guys, we're one step away from having our first law for control volumes. Does anybody out there that's still awake after this boring derivation session that we've just had, is there anyone that remembers what U plus PV is equal to? Here, let me call on somebody. If you don't remember it, how about Roxana? Roxana, do you remember what U plus PV is in this course?
I'm not sure.
That's fine. That's fine. It's the definition of something important. Let's pick on my friend Parker. Parker, do you remember what U plus PV is?
No idea.
That's fine. We'll keep picking on other people. Let's see. Cameron, this is the definition of something important. It's U plus PV. Cameron, do you remember what that is? He's thinking. U plus PV. It's a definition. It's a definition of something important.
U is, I think U is the internal energy, right?
Yes, U is internal energy. P is pressure. V is specific volume. And if you go U plus PV, that's the definition of one of our important terms that we have studied. We've studied it.
Enthalpy.
Yay, good going, Parker. The definition for enthalpy, can you guys see? I bet you can see that. It's U plus PV. That's if you use big letters. Now, if you use little letters, it's little u plus P little v. It's specific enthalpy. Okay, good going. Good going, Parker. You got that one.
Yep,
Go ahead.
I got it.
Yay. So we're at the bottom line now. Let me write it up here where everybody can see it. And then we'll work a problem. That'll be fun. Now, I went through all this to show you this equation. Here's where we are. Well, actually, we're not quite through. We got to divide by time. But see here, that U plus PV is a little h, so you can write it like this. That helps a little bit. And then you still have this stuff here. I usually put the kinetic energy there. Doesn't matter. Hope you can read my writing. There it is. Ta-da! There it is. See, what we've done is we've substituted. See that U plus PV, that's specific enthalpy. So we just put in specific enthalpy. I did this to show you guys where this specific enthalpy came from. We derived this thing, and I showed you how they did it. Sketched the derivation out for you. And now we have the first law. Well, what they like to do is divide it by time. So let's divide it by time, and we'll get it in the derivative form. You all know the definition of derivatives. Going back to calculus, this derivative is equal to the limit as time approaches 0 of E2 minus E1 over time. Didn't you study that in calculus? You subtract these and divide by time and make the time get real small, itsy bitsy, and you got yourself a first ordinary derivative. Do you remember that, calculus students? That's the definition of what a derivative is. Here, let's put 3 lines there. Definitions are 3 lines, aren't they? Well, what we're going to do is we're going to divide this by time everywhere, and we're going to make the time get tiny and teeny and tiny, make it smaller. And so here's what you'll have. And this is the way they usually write the first law for control volumes. They go dE dt, and then they'll put a dot over this. And now we're talking about control volume now. They'll put a dot over that. They'll put a dot over that. They'll put a dot over that. Uh-oh, I ran out of room. I got lazy. I ran out of room over there. But we are now in possession of the first law for control volume. Now, the first one we're going to study here is the nozzles. That's the next topic, is we're going to apply this to nozzles. But before we do, did you have a comment or question about the first law for control volumes? If you do, now is a good time to ask it. Well, nobody said anything. And when nobody says anything, what that means to me is that you totally understand it. You understand it perfectly. And so you don't need to ask me anything. Or you don't have the faintest idea of what's going on. And I hope it's the first one. But we're going to do a nozzle, and I picked out a problem to do. I picked out a problem, and it's 416, and we're going to do 416 here in a minute. But first of all, let's whittle this thing down. Now a nozzle, you guys all know what a nozzle is. You probably have one on your garden hose. You screw this thing onto your garden hose and you turn on the water, and what it does is it increases the velocity. That's what nozzles do. They increase the velocity. That's why they have nozzles. The opposite of a nozzle is something called a diffuser. It does just the opposite. It decreases the velocity. And something you need to know about nozzles, they are what they call steady state devices. Now you have a certain amount of properties coming in, like the pressure coming in, specific volume coming in, specific internal energy, specific enthalpy, and all that. All those properties, temperature coming in, pressure coming in, but it's not changing. We're dealing with things that are not changing with time, but they are changing with the location. The pressure going out, the exiting pressure can be different in a nozzle. The exiting specific volume can be different. The exiting specific internal energy can be different. The exiting specific enthalpy can be different. The exiting temperature can be different, but not with time. If you run this nozzle for 10 minutes and then run it for half an hour, the exiting properties are the same after a half an hour. They haven't changed any. But they change with location. The temperature going in and the temperature going out can be different, but they're not changing with time. Does that make sense? And so if this is the total energy inside your control volume, that's your control volume, that's your nozzle. The total energy inside your control volume is not changing with time. And so this term will be zero. That will be zero. Now, another nice thing about nozzles is they don't have any heat transfer of any significance, so we can get rid of that. Isn't that nice? We don't have to worry about heat transfer of nozzles. If you have a nozzle, just assume that the heat transfer is zero. And you know what? Nozzles don't have any work or power. They don't do any work, and the environment doesn't do any work on them. So that's zero. Man, this is going to be easy, bunch of zeros. But you have to keep some of these terms. This is a keeper right here. The mass coming in and the incoming specific enthalpy. Now this kinetic energy, it's going to look like this. What that actually is specific kinetic energy. Here, let me refresh your memory. Kinetic energy, we all know and love, is 1/2 mv squared. That's kinetic energy. Well, what we had in here was specific kinetic energy. That's kinetic energy divided by mass. Now, if you divide that by mass, you'll just get 1/2 v squared. See it? 1/2 v squared. Nozzles don't change their potential energy. So here's what you're left with. Forget about the change in potential energy. And you got your equation for nozzles. Now they have that in your book. Let me show you where that is in your book. See if I can find that. The equation for nozzles. There it is. I found it. It happens to be on page 122 in my book. And here's what it looks like. I'm going to erase this unless you have a question. Well, if there's no question, I'm going to erase all of this, and I'm just going to write the first law for nozzles right now. And it goes like this. The first law of thermodynamics for nozzles goes like this. We've thrown out all the other terms. We didn't need to worry about the m dots because they're the same. Whatever the mass flow rate going in is equal to the mass flow rate going out. Here I need to write this per time. Here's the first law in general. In general, this is your first law. Here we'll write out the kinetic and potential energy terms. There it is. There's your first law. Now, you can put a control volume underneath all this. Control volume, control volume, control volume, control volume. We're dealing with control volumes, but after a while I get tired of writing control volumes under there. We know we're dealing, if you got a nozzle or a boiler or heat exchanger, we know we're dealing with control volume, so I'm not going to write it down. We know that's the first law for control volumes. We don't need to write down control volume on it. There it is. Now that equation, you will see it on page 122 in my book anyway. This is your first law of thermodynamics for nozzles. Now we're going to work problem, whatever I said. I forgot what I said. I think I said, was it? I said we're going to work problem 416. Now problem 416, if you look it up, they deal with 3 different gases. Let's just do one of them for right now. We just don't have enough time to do what we want to do in here. But we'll do it with helium, let's say. Let's say you have helium, okay? All right. Well, let me read the problem here. It says, a nozzle receives an ideal gas flow with a velocity of 25 meters per second. Okay, well, here, let me write that down. You'd have to go 25 meters per second, square it, divide by 2. What else do they say? And the exit, velocity, the exit's at 100 kilopascals. I really need to draw the device sketch. Here, let me do that. Let me draw this device sketch. Here's your nozzle. You've got helium, and coming in, coming into the nozzle, you have 25 meters a second. And exiting, you have 100 kilopascals 300K. But the velocity is 250. Do you see the velocity got bigger? It came in at 25 meters a second, but it goes out at 250 meters a second. And they wanted to know what the incoming temperature was. See, we're going to try to find the incoming temperature. That's what we're going to do. Supposing it's helium. Problem 416 wants you to do it with helium, argon, and methane. We could do it with the others if we had time, but let's do it with helium. Okay. Now on this one here, they give us the 250, so let's put that in there. There we go. There's our equation. Now, here's the problem. We don't know what HI or HE is. That's kind of a problem. But let's do a little algebra here and see if we can solve this. First of all, though, I want to look up something for helium. Go to the back and find me C sub P for helium. Where would that be? Let me shop around back here. There it is, helium. C sub P is 5.193. Okay, let me write that up here. C sub P for helium, I've got 5.193, and it's on page A.5, kilojoules per kilogram Kelvin. Okay. So what? What's that got to do with anything? Well, I don't know. We looked it up. Now watch this. Now we're going to do some algebra. We're going to go HE minus HI. See if you can follow this algebra here. Is equal to 25 minus 250 Can you get from here to here? Can you make it? And I'm going to wait till I hear an uh-huh. I didn't hear any uh-huh. I got to find out if anybody's still listening or if they all left me a long time ago. I need to know somebody's still out there. Let's see. Let's see if I can find one of my excellent students here. Megan, I'm always picking on you. Megan, were you able to get from here to here?
Yes.
Yay, good going. Now, you know what this is? This final minus initial. This is exiting minus incoming. But you know what that is? That's delta H. And we studied that. We know what that is. That's equal to C sub P delta T, isn't it? Yes, it is, Mr. Griffin. And we got the C sub P, don't we? C sub P is 5.193. But we don't have the change in temperature, dang. But it's 5.193 kilojoules per kilogram Kelvin times the final temperature, which we know. They gave us that. It's 300 minus the initial temperature. Okay, we have an equation now. We have some numbers over here on the left side of the equal sign. And on the right side of the equal sign, there's only one unknown. Look, there's only one unknown. We can find the initial temperature coming into this. What do they call this thing again? It's got a name. Let me pick on somebody. That thing has a name, and it's called, let's go to my friend Cameron. We'll pick on you again. I'm always picking on Cameron. Cameron, what's the name of this thing right here?
I'm not too for sure, to be honest.
That's fine. Cameron, that thing is called a nozzle. Cameron, do you have a nozzle that you can screw onto your hose and squirt water? Do you?
Yeah.
What is the purpose of a nozzle, Cameron? Why do you have that nozzle?
Increase of velocity.
That's it. That's exactly it. Do you see the velocity increase? It went from 25 to 250. That's quite an increase. And we have a lovely equation here. And we can solve this. Let me write it out carefully for you guys. I just need room here. I need some room to solve this. All right, now here's what we have. We have 25 minus 250 equals 5.193. I like this equation. It's only got one unknown. It's only got one unknown. See it? Look, we should be able to solve that. But there is one fly in the ointment here, guys. The units are wrong. By the way, if somebody just tuned in and they wonder, well, what's he talking about? We are doing problem 416 in your book for helium. It's a nozzle problem. And we know the first law for nozzles. See, this law, this is the general first law. That is the general first law. How do you spell general? Well, there we go. That is the general first law. Whereas what we're dealing with here is a very special first law that only works for nozzles. This works for anything. The first law, well, any controlled volume, that is. But the first law for nozzles is down here. And we got it. We're doing great. But there's a problem, and the problem is the units. Because it turns out that a meter per second squared is not equal to a kilojoule per kilogram. It's not equal to a kilojoule per kilogram. Can you see the kelvins cancel? The kelvins cancel, and you have kilojoules per kilogram. But over here we have meters per second quantity squared. It turns out that a meter per second squared is equal to a joule per kilogram. Let me see if I can show you that. And guys, a joule per kilogram, it's not equal to a kilojoule per kilogram. It's just not. So we have to do a little conversion of some kind to get it equal. But here, go with me here. That's a kilojoule. Well, you know what a joule is? It's a Newton times a meter. So a kilojoule is a kilonewton times a meter. Do you know what a Newton is? A Newton is well, you have K for kilo, and a Newton is a kilogram meter per second squared. You might remember that. Don't forget there's another meter, and you're dividing by kilograms. Can you see that the kilograms cancel? And what you have left over here is a kilogram. No, it's a kilo meter squared per second squared. I don't know if that made any sense, but I hope it did, because this is important. If I can't teach you anything else in this course, maybe I could teach you this, how to deal with units. And when you have an equal sign, you got to have the same units on both sides of the equation, or it's no good. So what we got here is meters per second quantity squared, but over here we have kilometers per second squared. We're going to have to do something. And here's what we're going to do. We're going to multiply everything over here by a kilo and divide by 1,000. Take everything over here, multiply by a kilo, and so you'll get kilos on the left and kilos on the right. And now if you divide by 1,000, you'll get kilojoules per kilogram Kelvin. Because we just figured that out. A kilojoule, I got lost there. What happened to the Kelvin? Well, it's there. Yeah, they canceled out, and the units will equal now if you'll multiply by K over 1,000. Okay, well, here goes. We're going to do it. You have to do that. Get your calculators. I'm going to shut up for a minute, and I want you to solve this, and I want you to find the initial temperature of your nozzle. On your mark, get set, go. Well, I have an initial temperature. I plugged all that stuff in. I got an answer. Let me pick on somebody here. That's fine. One of my most wonderful students. We're going to go to Bear. Bear, do you have that yet? Earth calling Bear. Earth calling Bear. Come in, Bear. Maybe he had to go take a break. We're solving this equation now. We have all the numbers except the initial temperature coming into our nozzle. What about my friend Aubrey? Aubrey, did you get that yet?
I got 6,257 Kelvin.
No, something bad happened, Aubrey. Do it again.
Okay.
That's okay. Something bad happened. So you got to do all this in one glob, and then you have to divide it by 1,000, Aubrey. Maybe I should do mine again. I could be wrong. Let Let me do mine all over again. Maybe I goofed up. No, I think I did it right. Let me pick on another one of my excellent students here. Maybe Spencer. I don't think I've picked on you all morning. Spencer, are you there?
Yes, I am.
Did you get that yet, Spencer?
I'm not sure if I did it right, but I got 301.15.
Well, that's close to what I got, but that's not exactly what I got. Spencer, I got 305.95 something or other. Kelvin. Do yours again.
Oh.
That's
I'll
what
do-
I got.
Anybody else? There's two of us now that have gotten that. Anybody else got that?
I got that too when I reworked it.
I bet it's right. I bet it's right. Here, let me draw you the picture here. It's just math. I know you guys can do this.
I
But
got
see,
that as well.
good. I'm glad to hear that. See, here's this here's this nozzle. And coming in, we have 305.95 K. And going out, I think we have 300 K. You know what? It cooled off, but not by much. Not by much. And we're doing the problem with helium right now. Now, what was I got lost. What was the pressure coming in? Just a minute. Let me see if I can find this. This was problem, oh gee. Does anybody remember what we were doing?
416, and I
Yeah,
think the
thank
pressure
you,
was
sir.
1,000 kilopascals.
Thank you so much. Coming in. What was the pressure coming in? They never said, did they? They said the exiting pressure is 100 kilopascals, didn't they? Okay. And they said coming in, the velocity is 25 meters a second, but going out is 250 meters a second. And they never did tell they never did give us the pressure coming in. I wonder if we could get it. I don't think we can. I don't want to go off on a tangent now, but we did a nozzle. We got 10 minutes. Let's do another one. Let's do another nozzle. And now this nozzle here is in English, senor. So we're going to do a nozzle in English. Here we go. I'm going to erase this unless somebody wants to say something. All right, well, I'm going to erase this and we're going to do another nozzle. Now this one, I believe I want to do 4104. 4104E. It's a English. 4104E, it's English. And I'm pretty sure I've done that, so I know what the right answers are, but let me double check. I don't want to lie to you guys. Okay, 4104. I think that's the one I want. Not in that pile. Let me keep looking here. 4104. Yeah, there it is. Now this one's air. Okay. Well, here let's draw the device sketch. We're dealing with air now. Okay. And let's write down the incoming and exiting terms for 4104E. Here we go. We got to learn to work in English too, you know. You might get a job in the United States. We use these English things here in the United States. There it is. Jet engine flow of air at 1800 Rankine. Let me write that down. 1800 Rankine, 30 psi, coming in. And 90 feet per second coming in. Exits at 1500 Rankine. Now it cools off. That's what nozzles do. So do turbines. They always cool off and the pressure goes down. The pressure here is 13. Pressure went way down. Look, it was 30 and now it's 13. What is the exit velocity? We're going to find the exit velocity. We know the incoming velocity. See, there's the incoming velocity. They want us to find the exiting. Well, we don't know what it is. We'll put a little mystery cloud around it. We'll try to find it for them. Okay, now this is the general first law, but for a nozzle, the way the first law works for a nozzle is like this. This is in your book. I showed you the page, but I forgot what it is. But that's it. That's the first law for a nozzle. And that is on page, I'll tell you where it is. It's on page, well, it's on page 122 in my book. I see it on, I see this equation on page 122. There it is. That equation is the first law for a nozzle. See, this is the first law for anything. Nozzles, boilers, pipelines, whatever you want. This one only is good for nozzles. Okay. Well, we're going to do some algebra now. See if you can get to here with me. Can you? I think I did that wrong. I did do it wrong, didn't I? Now stare at that. Did I get that right, algebra students? Yeah, I think I did. Okay. Now, see, we know these. We can plug those in. And you know what that's equal to? That's equal to delta H, isn't it? Oh, yes, it is, Mr. Griffin. And for air, isn't that equal to C sub P delta T? Oh, yes, it is, Mr. Griffin. Well, okay. And you know what C sub P is? It's 1004. Now, wait a minute. Wait a minute. Auga. We're in English, senor. In English, it's different. It's, oh, gee, I'm trying to remember what it is in English. I think it's 0.240 BTUs per pound mass Rankine. But if you're not sure, we could always look it up. Just go to the back and we'll look it up. Go
It's
to the
on
back.
table F.4, and that looks right.
I got it right?
Yeah.
Table F.4. Thank you. Well, I'm going to look and make sure here. I like to see stuff with my own eyes here. F.4. Okay. Table F.4. Having trouble finding it. But we don't give up easy around here. Yeah, here we go. Tables. F.4. Oh, I need to be in the English tables, don't I? Yeah, there we go. English, senor. And for air, it says, still don't have it here. There it is. Air is 0.240. By Jove, we've got it. Ta-da, that's it. Table F.4, just like my excellent student was trying to tell me. Well, we made some, and we know what these are. Here, let me write all this stuff down. You understand all that? And what about our PV diagram? Let's do our PV diagram. Now, where am I going to do it? I don't have much room here. There's a little room over here. We could do it over here. Now, here's the rule on these PV diagrams. If you have a process, then sketch the process on a PV diagram. Unfortunately, I graded 3 or 4 of my wonderful students' homework. They did everything right. Oh, they did a good job, but they didn't draw a PV diagram with a process on it. Have I mentioned to you that the key to surviving this course, and well, to mastering the course, is to understand the PV diagrams? I think I've told you that. Let me tell you again. Here's the key to really understanding this course, is to being able to draw the processes on PV diagrams. And I expect you to do that. I do it. I'm going to do it right now. I'm going to draw a PV diagram for this, this nozzle. Now it's going to go from 1800 to 1500. So we're going to put some nice curved isotherms here. This can be 1800. This can be 1500. Rankine. Now the pressure went down from 30 to 13. It went down from 30 psi to 13 psi. Here's state 1. Here's state 2. There's your process. From 1 to 2, there's an arrowhead. I expect you to always, if you have a process, to always sketch the process on a PV diagram if you want your 4 points. I think I had to give 3 or 4 of my students 3 points because they didn't do that. Well, do it. Make me happy. There's your PV diagram. Now let's write the equation and we'll solve it and we'll get our final velocity. And the final velocity should be bigger. It should be bigger than 90 feet per second because that's what nozzles do. Here, I'll write the equation. Just need some room to do it in here. Here we go. There, I've given you my sermonette on PV diagrams. And now here's another thing. If there's a vapor dome, draw the vapor dome. There's no vapor dome on air. If you got air, don't draw the vapor dome. See how it works? If you do have a vapor dome, draw the vapor dome. If you don't have a vapor dome, don't draw the vapor dome. Air doesn't have a vapor dome. It just has those isotherms. They're hyperbolic things. Okay, here comes our equation now. We have, oh gee, I forgot I erased all my numbers, but I can find them again. Here we go. 4104, that's what we're doing. It comes in at 90. Yeah. And so we know it's 90 feet per second squared over 2 minus, well, we don't know what the exiting velocity is. That's what we're trying to find out. Equals 0.240 BTU pound mass Rankine times the change in temperature. Isn't the change in temperature minus 300? Can you guys all see that? It's minus 300, isn't it? So you're going from 1800 to 1500, so you got colder by 300. Yeah, there you go. Well, that looks pretty simple. But see, you can't just plug that in and get the right answer, because the units have to be the same. See, this is feet squared per second squared, and this is BTUs per pound mass. The Rankines cancel. But I'm sorry, those units are not the same. Now here's what you have to do to get those units the same. It turns out that a pound force is equal to 32.174 pound mass feet per second squared. That's in your book on page 9. You'll find that on page 9 in your book. We're almost through with this problem. We'll take a 10-minute break here in just a minute, and then we'll come back for some more fun. And here's something else. A BTU is equal to 778, something like that. I wonder if I did that right. Let me double check that. I don't want to lie to you here. I think that's right. Yeah, that's pretty dang close. I think it's a 1.7, but that's close enough. Now to get these units to work, what you have to do is you got to take everything over here on the left, everything, and you have to divide it by, you have to divide it by 32.174 pound mass feet per second squared. And you have to divide it by because see that'll give you foot-pounds. That'll give you pounds of force in the numerator. See, a pound of force is equal to 32.174 pound mass feet per second squared. And then you have to divide this by, running out of room here, you have to divide it by 778.17 foot-pounds force. That's equal to a BTU. I don't know if that made a lick of sense. But see, what happens is the foot per second squared will cancel the foot squared per second squared and give you a foot. And the foot times the pound force will give you foot-pounds. And then when you divide by foot-pounds, the foot-pounds will cancel out, and you'll be left with BTUs per pound mass. So you have to take everything over here and divide it by these numbers in order to get the same units on both sides. You might have to sit and think about that for a while. But what we're going to do is we're going to take a 10-minute break. We have our equation now. I hope you can read all my writing. And we're going to solve for the exiting velocity. Just divide everything on the left here by these numbers. Set it equal to this, and we'll solve for the velocity. And in 10 minutes, we're going to come back. We're going to get that exiting velocity. And then we got lots more to do. We need to do, oh gee. We need to do throttles, turbines, heat exchangers. We'll never get it all done, but we'll do the best we can. I want you to see if you can solve this. And if you need to take a break instead, that's up to you. But we'll be back in 10 minutes, and we're going to solve that. Okay, 10-minute break. Okay. I'm going to plug this in and see what I get for the exiting velocity. Here goes. I'm plugging it in now. Oh, no, wait a minute. See, that's an unknown. We don't know what that is, do we? Well, that doesn't scare us. We can solve this. I wonder if that's what I got when I did it before. Let's see. This was problem 4104E. I got a different answer this time. Maybe I better try that again. Okay, here we go. We're going to try it again.
Is our change in temperature supposed to be negative, or is it supposed to be the 300, not negative 300?
Well, it got colder. It got
Okay.
colder. Yeah. The change in temperature should be negative 300. I believe we did that right. Yeah. I think we did that right. Okay. I got a different answer. I get a different answer every time I do this. How about you guys? Okay, well, let me try one more time here. I'm not going to give up quite yet. Well, I keep getting different answers for that. Different from what I got when I did it before. Let me double check it here. I don't want to give you wrong info if I can possibly help it. Yeah, I think I checked that. Trying to find 4104E. Yeah, here it is.
I got 107.6235.
What are the units?
Should be Rankine.
Aren't we solving
Well-
for the unknown? The unknown is velocity.
Ah, yeah, hold on.
We know what the change in temperature is.
Wait, no, it should be feet per second.
Yeah, it should be feet per second.
Yeah, because the Rankine's canceled out on the right side.
Yeah, I think they go bye-bye. Okay. That is right for air. It's 0.24, and the temperature change was that. And you have to divide all this by this to get the units to work. I think that's right. Let me try it again here. 0.24 times 300. Well, it's negative. And then when you get through, though, you have to multiply by this stuff. 32.174, 778. And then what do? Well, you do some algebra. And then what do? Well, I think you have to multiply by 2 and to take the square root. Well, I keep getting the same answer, guys. I keep getting the exiting velocity is 1900 feet per second. Does anybody get that?
I
Out there?
got 2.34.
You got 2.34?
I got 230.34.
230.34. I don't think that's right.
I'm getting 1900 as well.
I got 1900 feet per second. Okay, well, I bet that's right. See, it speeds up.
Do you multiply or divide by 32 over 778?
Well, what I would do is we're dividing the stuff on the left here of the equal sign. I would multiply that times this stuff over here on the right is what I would do. Multiply this times all of this. And we probably should write it out step by step. But I'm getting 1900. What bothers me is I did this yesterday and I got a slightly different answer, but I don't want to spend all of our valuable time haggling over some goof up in my algebra here. Oh, I know what the difference is. I know exactly what the difference is. I used a different model, which is okay. Now, instead of using this model here, Instead of using C sub P delta T to get your delta H, see that's what I did. I used a different model. I just looked these up in the back of the book. And I couldn't figure out, well, why did I get a different answer yesterday? Well, here's why. If you go to the back of the book and look up air under, it's English though. You got to go to the English section and you look up air, here it is. And instead of using this model here, see, there's different models. And I've told you about different models. You could just look these up. Whoops, this should be 2 minus 1. And so this would be at the 1500 temperature. Now the 1500, yeah, the 1500 temperature is, well, you have to look it up in the back. And what I got was they don't have a 1500 in the back. You have to interpolate. Now let me get it. 374.565 plus 385.177 divided by 2. I'm getting 379.9 minus what it is at 1800. Now they do have 1800 in the back. It's 449.794. Ran out of room here. Dang. Just rounded off to 8, I guess. I got this on table F.5. It's a different model. In other words, I think this is correct, guys, if you use this model. Now, if you use this model, then this number here should equal, here, let me write it down for you. Subtract the 449.8. Instead of using this number here, use, well, it's not technically equal, but use minus 69.9. Now, if you'll do that and you'll solve this, you'll get the answer I got yesterday. And let me do that and see what happens. And then you have to multiply by 2 and take the square root. Okay, that's still not what I got. Wait a minute. Should be 369. Let me do that again. 1500. 364 plus 374.565. Yes, it's 369. It's 369.3 minus the 449.8. Okay, using the model F.5. I've told you about those different models. 449.8 was it? 1800, 449.794. Okay. All right. And that gives me a minus over here on the right. And then what do I do? I have to multiply by all this stuff. And then what do I do? Subtract this squared. Times 2. Square root. There you go. Now, if you use the other model, what you'll get is this here. Now this is a better model. This model here is a better model because these temperatures are very high. They're not room temperatures. We're using a C sub P at room temperature. And I was telling you about that. Put an unhappy face on this model and put a happy face on this model. This answer is better. But if you did this on an exam, let's say, or a quiz or something, I would give you credit. It's a good model. It's just not as accurate as all. So there we have it. We've done a nozzle in English, and we've done a nozzle in SI. Kind of got hung up on the algebra there a little bit, but I reminded you that there are different models. Some are more accurate than others. But several of you got 1900. And that's what you'll get if you use this model here. If you use the model F on table F.5, it's more accurate, and you'll get this answer here. Well, I'm pretty happy with that. Did we have any questions before we do our last little project for today?
Do you think you could write the process in a way that's a little more understandable? Because I had to step away for a second, and looking at this, I don't understand anything that's going on, and I'm not getting anything close to 1900.
Okay, thank you so much. Thank you for asking. I'll write it out to where it's possible it can make more sense. And now, who was that asked? Was that Spencer?
Yes, sir.
Okay, Spencer, I'm going to make a, I need room to do this, Spencer. So I'm going to write it here. And I'm going to write this out here now. And it's possible this will make more sense. I don't know. We'll try. We're going to have to, you're taking notes. I know what I got for my answers. I can look those up here in a minute. And this time I'm just going to put this all over here on the right. Okay, now we're going to look at these units. Now, you know what the units here on the left are. They're feet squared per second squared. You can see that. See, this is feet per second. And when you square it, you get feet squared per second squared. So over here on the right, it's got to be feet squared per second squared. Well, look here. The Rankins cancel. They're gone. See those Rankins? We just got rid of the Rankins. Now you see this pound mass. Oh, it cancels. We got rid of the pound mass. See that pound mass? It's bye-bye. Now, do you see this? Got lost there for a second. Do you see this pound mass? Got too many feet in there. Oh, here we go. This should say 778 foot-pounds per BTU is what it should say. Now, do you see that BTU? It cancels, it's gone. We got rid of the BTUs. Now, do you see this 32.174 pound mass feet per second squared? That's equal to a pound force. Well, look at here. See that pound force? It cancels. And here's what you got left. After you cancel out all that stuff, you have foot squared divided by second squared. Well, that's what you got over here. You got foot squared divided by second squared. Now I'm going to put all this in my calculator, and we're going to get the answer. Now, this is not the best answer because it's not the best model, but it's a good answer. All right, I'm going to multiply all this jazz. Here goes. Okay, I got a humongous number over here on the right side of the equation. This is what I have. Did I write that down right? I think so. Now on the left side of the equation, I've got this here, which is, hang on, that's 90 squared divided by 2. That's 4050. Okay, I've whittled it down to this now. Now I know that you guys have taken enough algebra that you can take it on home from there. And that's what I'm going to do now. Here goes. And well, I would have to subtract the 1802652, right? Yeah. And the minuses go bye-bye. Multiply by 2, take the square root. And boy, Jove, when you get all through, Spencer, you get 1900. Well, it really rounds off to 1901, but we won't quibble over that. Feet per Spencer, are you okay now? Do you feel a little better?
Yeah, I just got lost with some of the unit conversions, and it looked like on the left side of above, it looked like it was 32.74 divided by 778.17 because of like my internet quality right now. So that really threw off all my calculations.
Yeah, that threw it all off. Yeah. You might wonder where I got that 32.174. Let me share where that comes from. You go back here in the back and you look on page, yeah, there it is. It's Appendix A4. If you look on Appendix A.4, you'll see that 32.174. Well, you can also find it in the front of your book. I think I told you on page 10 or 9. Yeah, you can look it up on page 9 at the very front of your book. It says a pound force is equal to 32.174 pound mass feet per second squared. Well, that was a lot of fun. Anybody else? And do you understand? We got two different answers. We got this answer here. I'll put an unhappy face on that, but it's a decent answer. But it's using the specific heat at room temperature. We don't have room temperature. 1800 Rankine. I think that's a little hotter than room temperature, folks. If you use the tables in the back, I told you the page number. I got lost here. I think it's F.5. They have integrated those specific heats, and you get an answer of, it's more like 2000. I forget. Yeah, it's the best answer is 2010 feet per second. We'll put a happy face on that. There you go. 2010. Okay, well, we had a lot of fun with the nozzles. Now we're going to do a heat exchanger. We got time. We're going to do a heat exchanger now. Is there any comment or question? Again, I'm listening. Okay, well, we're going to do a heat exchanger now. Now this one is problem heat exchanger. Okay, totally organized here. Yeah, this is 462. We're going to do a heat exchanger. But I need to say goodbye to all this. I'll keep my general first law up there. We don't want to lose it. But we're going to do a heat exchanger. Now, heat exchangers are big business in Tulsa. There's people that make a living dealing with heat exchangers in Tulsa. But there's a couple of things you need to know about heat exchangers. See, condensers. You got condensers in your air conditioner. That's the outside one that blows the hot air. If you ever walk by outside your friend's apartment, the air conditioning is running, and man, it's hot already. 100 degrees out here, and that thing's blowing air that's even hotter than that on me when I walk by it. Well, that's a heat exchanger. The condenser is a heat exchanger. And heat exchangers are isobaric. You need to know that. We're going to do a problem. It's 462 here in a minute. And you need to know that heat exchangers are isobaric. Heat exchangers are isobaric, and I hope you know what isobaric means. Here, we'll pick on somebody. Let's see here. We'll pick on my friend. Need to go up here a little higher on this. Yeah. Bear, what's a heat? What does isobaric stand for, Bear? Unmute and tell me what isobaric means.
Isn't isobaric constant pressure?
You got it. Jolly good. Proud of you. It's constant pressure. It's exactly what it means. Now, heat exchangers, they're constant pressure, but they're also something else. They don't theoretically, they don't exchange heat with the environment. The heat exchange is all internal. Now, on this problem here, this is 462 here. I'll draw you the device sketch. We'll draw the device sketch. They've got cooling water coming in here. They label this state 3. It's cooling water. It's coming in here at 15 degrees Celsius. And 150 kilopascals. But see, it's going out at state 4 at 80 degrees Celsius. It's cool water going in, and what it is, it's pipes like this. There you go. And you have hot air blowing through here. We're going to call this state 1, and this is air coming in. And the air is coming in at 500 K, which is pretty hot, and 200 kilopascal. But the air is going out at state 2. And see, the air is going to cool off to 330 K. Well, that's quite a lower temperature. It came in at 500 K, but it's going out at 330 K but notice it's at the same pressure. The air came in at 200 kilopascals. The air goes out at 200 kilopascals. So it's isobaric. The cooling water comes in at 150 kilopascals, and it goes out at 150 kilopascals. It's isobaric. So there's your device sketch. Now there's a heat transfer from the hot air to the cool water, but it's internal. There is no heat transfer with the environment. What we're seeing here with the environment, the heat transfer is 0. That's the other thing you need to know about heat exchangers. They're isobaric, and the heat exchange is 0 with the environment. All the heat exchange takes place inside the heat exchanger. Okay, well, let's read the problem. This is 462. Let me find it here. Let's see, 462. Air energy recovery heat exchanger shown, blah, blah, blah. You guys could read that. Used to heat water flow at 15 degrees, 150 kilopascals to 80 degrees. Why would you do all that? See, there's the 15 degrees coming in and the 80 degrees going out. The energy is taken from a 2 kilogram per second airflow. Well, we didn't write that down. Let's write that down. See, that's your mass flow rate. It's 2 kilograms per second. The air coming in is state 1. and it going out. Of course, it'll be going out. It's going to be 2 kilograms per second going out. That's your mass flow rate of your air. It goes out at 2 kilograms per second. All right, and it leaves at 330 K. We got that written down. Both states at 200 kilopascals. That's because it's isobaric. They want the flow rate of the water. They want to know what the mass flow rate is of the cooling water. Okay. Well, we have drawn the device sketch, and now we're going to draw the PV diagram. So let's do it. Now you're going to have 2 different PV diagrams. One of them is going to be for the water. And the other one is going to be for the air. It's kind of hard to put them on the same diagram because everything's so different. You have to make 2 diagrams. Now, if you have water, you're going to have one of these vapor dome things. Because see, water can condense to liquid. Well, it goes in as all liquid. You know what? That's all liquid. Now going out, I'll have to think about it. I think it's all liquid too. So in other words, we're going to be over here. They call this compressed liquid. You're going to be in this compressed liquid region for the water. But now the air, you don't have a vapor dome for the air. What you can have is you can have isotherms. See, what are you doing? You're coming in at 80 and going out at 15. Boy, that's a big difference, is it? No, that's not right. You're coming in at 500 and going out at 330. Okay, so here you go. We'll draw the 500K. And then we'll draw the going out at 330K. Now it's isobaric at what, 200 kilopascals? Well, is that right? Yeah, the air is at 200 kilopascals. So we'll just fake it and put it right here. Here you go, 200 kilopascals. We call that state 1 for the air. It's a isobar. State 2 for the air. Ta-da! We just did it. We just drew the, we just sketched the process. Now remember the rules. Here, let me write it out for you. If there is a process, then draw the process on a PV diagram. That's the rule. Whenever you have a process and you want to really master this class and you'd like to get a 4 instead of a 3 on your homework, then draw the process on a PV diagram. Well, I did. Look, there's state 1, there's state 2. I drew the process. It happens to be an isobar in this case. I even put a little arrowhead on there so I'll know which way I'm going. Of course, with a 1 and 2, that tells you you're going from 1 to 2. But what about the water? Well, we got to think about that. Now, the water is at comes in at 15 degrees and it goes out at 80 degrees. Well, all right, let's see if we can draw those. 15 degrees and 80 degrees. We can put 80 degrees up here someplace, I guess. Now the 80 degree, there's the 80 degree Celsius isotherm. It looks like that. Everywhere on that is 80 degrees Celsius. It's an isotherm. That's coming in. But now going out, no. I think I just goofed up. No. I'm doing it right. Going in, it's 15 degrees. Well, see, 15 degrees is like this. I think I did that right. Here we go. 15 degrees. This one's a 15 degree isotherm. Everywhere on that line is 15 degrees Celsius. Now, let me go to the tables and look up some stuff. Go back to the water table with me and look up water at 15 degrees. Okay, I'm looking now. 15 degrees. Okay, I finally found the table that I want. Here's 15 degrees. This pressure right here is 1.705 kilopascal. And this pressure right here at 80 degrees is 4739. Now I'm going to pause a minute and I want to make sure that everybody can find those numbers, the 1.705, the 4739. It's table B.1.1. I'll shut up. B.1.1. And I need to hear 2 or 3 students say, uh-huh.
Yeah, I found it.
Yay! Good going. I need another one. I need another student to find those numbers on table
I
B.
found those numbers.
Good going. Good going. Well, that's enough. Now, what we got is 150 kilopascals. Well, you know what? 150 kilopascals is bigger than 1.705 kilopascals. In fact, it's bigger than 47.39 kilopascals. You know what? We're in here someplace. Remember, this is logarithmic. They don't necessarily go linear. And I think we're going from 1 to 2. There's state 1, and there's state 2. See, state 1 is 15 degrees Celsius and 150 kilopascals. There it is. We know it's isobaric because the pressure stays, look, the pressure stays the same. That's one of the main things that we learned about heat exchangers. They are isobaric. And so state 1 is 150 kilopascals, 15 Celsius. State 2 is 150 kilopascals, 80. There it is. And you know what? It's isobaric, but you're in the compressed liquid region. We have drawn the two the processes on PV diagrams, haven't we? Isn't that the rule? If there is a process, then draw the process on a PV diagram. We're always going to do that. We're not going to forget. Now, if there's a vapor dome, draw a vapor dome. If there is not a vapor dome, don't draw a vapor dome. Fair enough? So we have done a lot so far on this problem. If you just tuned in, wondering what we're doing today, right now we're studying problem 462. It's a heat exchanger. Now we've done the device sketch. There it is. Ta-da, there it is. And look, we've labeled it. We've put in state 1, 2, 3, 4, temperatures and pressures. We've labeled it real good. And we've done the PV diagrams. There we go. Look, we've labeled them too. We put in isotherms. We've put in pressures. We could even put in volumes, but I was too lazy. I didn't bother with the volumes. But we put in temperatures. Now what's next? Well, let's see. We did the device sketch. We did the PV diagrams. What's next? Well, what's next is we're going to use the most important equation in our course. Now let me pick on somebody here. I'm going to ask them what the most important equation in our course is. And let's see. We'll go to Aubrey. Aubrey, what is the most important equation in our course?
I'm blanking right now. Delta energy equals Q minus W.
Yeah, that's it. What's the name of that?
The first law of thermodynamics.
Right, Aubrey, you got it right. That the most important equation in our course is the first law. Now, here's the thing, Aubrey. There's different versions of the first law. I haven't shown you all of them yet, but one of them is what you quoted. The delta U equals Q minus W. That's one of them. But see, we can't use that one. That one is for control masses. We can't use the one for control masses because we don't have a control mass. We have mass going in. In fact, we got water going in and out, and we got air going in and out. That's not a control mass. So we have to use a different version of the first law of thermodynamics, and it's this one here. Do you see this one here? This is the general equation for the first law for control volumes. Now what we're going to do is we're going to write the first law for control volumes for this heat exchanger. I just need a little room to do that. I might have to sacrifice some stuff here. I hate to sacrifice these beautiful diagrams, but I need the room because I need to write that first law. They want us to find something, and I think it's they want us to find the mass flow rate of the water. And we can't do it without writing that first law. So let me make a little room here, and here we'll go. We'll get it. Whoops. There, there's lots of room there. All right, now here's what we're going to do. We're going to write what this is. Now this is the the rate of change with respect to time of the total energy inside our control volume, and it's 0. See, there's an equal sign, and on the left of that equal sign is a 0. Now, why is that 0? Now let me pick on one of my other wonderful students. We'll go down, we'll pick on Stuart again. I'm always picking on Stuart. Stuart, why is the rate of change of your total energy with respect to time 0? Stuart, why is that?
I'm not sure.
Well, Stuart, the reason is that none of the properties are changing with time. Do you see this temperature coming in, 15? Wait a couple hours, the temperature coming in is still 15. In fact, wait a couple of days. This heat exchanger is working for weeks, all right? And it doesn't change. That 15 degrees doesn't change. And what about the pressure coming in? Well, it's the same too. In fact, all of these properties coming in and going out don't change with time. And that means that nothing's changing with time. The thing, the velocities and the temperatures, the pressures, nothing changes with time. It's 0. They got a fancy name for it. They call it steady state. You've got a steady state. That means nothing changes with time. Now, and let's see, after Stuart, it's Spencer. Spencer, I'll pick on you next, but I don't have anything to ask you yet. So just get nervous. Okay, so that's 0. Now on this Q dot, hey, I got something to ask Spencer now. See that Q dot? That's the time rate of change, or it's the heat transfer rate from or to the environment from your heat exchanger. Now, Spencer, what is the heat transfer to the environment or from the environment? What is it, Spencer? Go for it.
0 in this case.
Yay, good going, Spencer. Proud of you. See, there's 2 things you need to know about heat exchangers. One is they're isobaric, and the other is they don't exchange heat with the environment. There is no change of heat with the environment, so that's 0. Now, wait a minute. I'm going to find another wonderful student here. Just a second, if I can work this thing. Yeah, here we go. Roxana, you're next. I'm going to ask you something, Roxana. Okay. Roxana, this term right here stands for power. What kind of power is involved with a heat exchanger, Roxana? Do you have to plug them in? She's thinking.
Wait. Yeah, I'm thinking.
That's okay.
I'm not sure, like, is it like thermal power or?
Nope, there's no, you don't have to plug the heat exchangers in. The power is 0. They don't give you any power. They don't do any work. They just have water and whatever going in and out, but they don't do any work. They don't spin any water wheels or turbine blades or anything like that. They don't provide power and they don't use power. Now, your air conditioner has to be powered. You have to either plug it in or use your motor of your car to run the power for your air conditioner, but that's not for the evaporator and it's not for the condenser. That's for the compressor. Your air conditioner it's got a motor and it requires power, but the condenser doesn't. And see, you're condensing. Dang, I hated to erase those wonderful PV diagrams, but didn't didn't we have one of them that was going to the left? We had one of them that was going to the left. Now let me see if I can find where I did that. What are we doing? We're doing 462. We're doing 462, right? Let me see if I can find. I hated to erase that. I needed that to see what I was doing. Now I can't find it. Dang it. Let me keep looking. I'm not going to give up yet. 462. I'm trying to find 462. And we'll finish this off. How are we doing? Oh, gee. Oh no, we're running low on time. Oh no. Well, you guys have that. You guys have that that PV diagram that I erased. Let me see if I can reconstruct it from memory. It was a deal like the water was doing this, wasn't it? Was the water doing that? What about the air? The air was going. Was it going like that? From I got lost. I got lost. The water was going. I shouldn't have erased it. The water was going from 15 to 80. I think that's the water. And the air was going from 500 to 330, right? Yeah, it was doing that. Okay. Never mind all that. I was just forgetting what I was doing there for a minute. We only have about 3 minutes, and I might not be able to finish this, but here's how you finish it. In case you have two incoming things, you have to put a summation sign here. And in case you have, in our case, two exiting things, you have to put a summation sign here. So these are all zeros, but you have two summation signs here. You have a m dot for the water, and I think you can throw away the other terms. I don't think you need them. And then you have an m dot for the air. And then you have an m dot for the water. And then you have an m dot for the air. And that's it. See, we're throwing out the potential terms because it's not going up or down. Oh, gee, we only have a couple of minutes left. It's not going, this device is not moving. It's just sitting there. And so all you have to worry about is these enthalpies. And these are all zeros. Now, we know what this is here for the air. Didn't they give us that? Yeah. They said the air was 2 kilograms per second. That goes right here. We know what that is. So we know the mass flow rate of the air, it's given. See, this is what we're supposed to find. We're supposed to find the mass flow rate for the water. That's what we're supposed to find. Okay, so we could rearrange this algebraically and it'll look like this. The mass flow rate for the water is equal to H. Can we put that over on the left? A little algebra trick there, students. And over here on the right, we'll have our 2 kilograms per second for the air times the HI minus the HE. Now for the air at 500 and 330, I think we could look those up. Let me show you what table that is. Oh, gee. I don't have time to show you what table, but you've seen it before. And I'm talking about the happy face model that we use on another thing today. Yeah, hey, that was nice. One of the students wanted to form a group for the class. That's an excellent idea. Hope you guys can do that. Now these, guys, you can look these up in the back of the book on the air table in the back. And you can find this for liquid water by going C delta T, but you have to use the C for liquid water. And I think it's 3.18. Oh, but oh no, our time is, oh, it's so sad. We're just starting to have fun. But what I'm telling you is you can get this. And the only unknown that you're going to have is the mass flow rate of the water. And you can get it from your first law of thermodynamics. But you have to use this first law, only there's 2 terms here and 2 terms here. Well, we've had a wonderful time together. You have some homework and you have a due date. If you'll go to Blackboard, it'll tell you what the homework is and the due date. And I will grade it and put it in the grade book. Okay, guys, here's your last, we're going to end this.
Oh, I have a question.
Go ahead.
Did you ever check to see if you got my emails I sent you last week?
Now, who are we talking to?
Spencer.
Spencer. Oh gosh, Spencer, I don't remember. What did you need to know on those emails?
I was asking questions about my process for one of the homework assignments that I've gotten back and I missed a few points on. So I'm just wondering, like, what I really could have done differently. So that was the purpose of the email I sent before the assignment was due.
I will go back and see if I can find that. But on the homework, if you didn't get a 4, I usually write some nasty little note there.
Yeah, I got no comments on that assignment.
Oh, I didn't give you anything. Well, I'm starting to do better on that, Spencer. I'm starting to write down, like a couple of students didn't do a PV diagram. So I said, hey, there's no PV diagram. So they got a 3.
Yeah,
But
you did that on one of my assignments, but not
yeah.
on this most recent one where I was actually having problems.
Well, let me go back and you can try email me again and I'll email you back. But I'll look. Anything else, anybody?
I sent you a couple emails as well.
Say that again, please.
I sent you a couple emails too.
And now who is this that I'm talking
Parker.
to?
This is
I'm sorry?
Parker.
Parker. Parker,
Yeah.
I'm gonna look at my email here in a minute and see if I can find any from Parker. I will.
Okay.
Anybody else?
Yes, I have a question. I can't see your screen right now, but at the general equation up at the top, the one we were using,
Yeah.
where it goes hn plus velocity over 2 squared plus, what is that last term?
HN plus
H,
4
yeah,
velocity over 2 squared. Oh, that's GZ. What that is the specific gravitational potential energy. You know that gravitational potential energy is mgh. You learned that growing up in school. We can't.
Yes.
And is this Megan? Is that who I'm talking to?
Yeah.
Megan, we can't use H in this class for height. So we're going to use Z for height. Now, if you want if you want the little PE, you have to divide by mass. Now, if you divide by mass, you'll get GZ. And that's, I think that's what you're asking me about. It's
I think so.
GZ. Yeah.
Okay, it just looks like an M and a Z on my screen.
Oh, it's my lousy writing, I'm afraid. We'll try to do better. Anybody else? Good questions, though. Anybody else? Okay. 5, 4, 3, 2, 1. Goodbye.